In the last part of the lecture, we will connect the motion planning with our multi-goal planning in a multi-goal motion planning. And we will introduce the problem. So we look for the collision-free path. We already see the multi-goal planning in a polygonal domain. There was the simple collision-free shortest path, considering, for example, visibility graph. But we like to actually have the same for more advanced motion planning. So we actually need to solve the solution in the configuration space, not directly in the workspace. So for my part of the research, of course, I am motivated by high-dimensional planning for such a crawling robot. And this is an example of solution, simultaneous solution of this TSP on top of the configuration space. But there are hidden simplifications. The multi-goal motion planning is a problem where we consider the 3D environment. And within this 3D, we represent the obstacles as a set. And that provides us the notion for the configuration space as the robot has some shape, it is collision free if there is no collision with the obstacles. So that provides us the C free, and you should be aware that C free is C without the C obstacles, and C obstacles are the collision. The configuration of the robot with the collision with the obstacles. But instead of point to point, we have n goal locations, and we have the collision-free path. And for us, the multi-goal path tau is admissible if it is a mapping. Okay, it's this mapping from 0 to 1 in C3. It is closed. And there are endpoints on this path such that these points are within a sufficient distance to the goal location. So basically we have some goal location, and because we are not expecting to precisely visit that, so if we have a trajectory or path that pass these locations within the epsilon, we will call, okay, this is admissible solution for us. And of course, we are looking to find a path, a feasible path that is admissible. Multi-goal paths, not speaking about the optimality, but of course we also like the optimal path with the minimum cost. There are basically three class of approaches to multi-goal motion planning. The first is proposed by Mitul Saha in 2006, and it is based on a solution of the TSP, of the underlying TSP, as a minimum spanning tree. And the first, we consider we have these locations we would like to visit, and we consider Euclidean distance of our roadmap, and we find the minimum spanning tree. Let's it be like this. And now we have the MST-based solution of the TSP, and we ask optimal solution of the motion planning problem, which will provide basically some avoiding obstacles. It will be longer. So the MST is no longer MST, and we need to rebuild the MST, and we are continuing this until the MST will represent the edges will represent the solutions of the motion planner. That's one of the approach. The other approach, Cyclops, synergistic combination of layers of planning. So we can consider that the road planning is on one layer, very let's say relatively sparse roadmap with the goals, and we update the cost of the edges connecting using the trajectory planning. The two other parts how to address is that we can expand the roadmap, and we have two approaches. The first one is motivated by applying the unsupervised learning for TSP. So we, on top of some roadmap, using Euclidean distance for the connections that are not known, we apply a solution of the TSP, and where we have, once we have this solution, we actually expand in that promising idea. So it's actually find the MST similar to that, but it's on a different principle, and it can also be deployed on this traveling robot, but that's just a demonstrator that such a path can be found. And the last method I'm aware of is steering of the p4m star expansion using variable neighborhood search. So you already heard about the variable neighborhood search, and it is in the domain of orienteering problem, and we call this problem physical orienteering because we consider some realistic constraints, that we have the obstacles, we have the model of our flying drone, and basically here what we combine is that on top of the roadmap we run the variable neighborhood search, and the variable neighborhood search informs the sampling based part about adding more samples in particular area, and vice versa. Once we have the more samples, we have updated cost, usually shorter cost length of the trajectory, and then we inform the variable neighborhood search, okay, this is shorter, so rewrote the solution of the orienteering problem. And we also deploy this on the real flying drones, just to show, okay, it is sufficiently realistic that can be deployed. And in that particular day, that was quite windy, as you can see in these artificial obstacles, because sometimes something wrong can happen, so we don't like to destroy the drones every time. But this means that there is overflying drone that is capturing the scene. It's also moving in the wind. And this just demonstrates that, okay, this is sufficiently realistic to find a plan that can be executed by a real drone. So now let me summarize this lecture. You should be aware now that there exists a randomized sampling based method. You should be aware of two fundamental approaches, the probabilistic roadmap method and the rapidly exploring random trees. There are also the expansion trees and so on. And definitely you should be aware of this notion of rapidly exploring random graph, because it's related to the properties of sampling-based motion planning algorithms. That is a path, what is the collision-free path, what is a feasible path, what is admissible path, what is feasible path planning and optimal path planning, what is probabilistic completeness, and how it is related to strong delta clearance and robustly feasible path planning problem. Regarding the optimality, in a sampling-based or randomized sampling-based method, we are speaking about asymptotic optimality, which is related to weak delta clearance and homotopy, and robust optimal solution. There are these extensions of the p4m and RRT. This is RRG, p4m star, RRT star. You should consider that there are improvement algorithms for randomized sampling-based methods. It is inform RRT star that use some estimates, some heuristic to actually reduce the search sampling space. You can improve the performance by batches of samples and reusing the previous search using lifelong planning A star. You can employ local search strategy to improve the convergence speed. But it's not particularly, I will not, for the exam, I will not ask you about details, about the main principles that are involved. And this is a nice example how you can improve the performance. And also if you have a new solution, new algorithm that you can expect, okay, it will be improved maybe by myself or maybe someone else. And definitely planning in dynamic environments that you should be aware there is something like RRTX, and also it is improved later by nowadays approaches. And considering data collection planning, robotic information gathering, you should be aware that multi-goal motion planning is a little bit more complex because we need to include these challenging problems and algorithms that may not be that fast. But it's a further variant of a robotic TSP. And in the next part, you will continue on game theory in robotics. So enjoy the rest of the course.